models for treatment effects. We're going to talk about models for homogeneous treatment effects when we're trying to estimate some sort of average treatment effect. We're going to talk about models for estimating heterogeneous treatment effects when we want to understand how the effects of a particular treatment or intervention vary across different people or units. And we're going to talk about Bayesian models for those things because in my experience, that's a pretty reliable way to make inference, and the best performing methods we have are Bayesian. But you don't necessarily need to go full bore on Bayesian inference to get something out of this talk. A lot of the stuff we're going to talk about is sort of more general considerations when we're trying to do this. And I sort of split the talk up into three pieces. So the first piece is how we parameterize our models. The second piece is how we pick our prior distributions. If you're more of a machine learning type, you can think about that as how we apply regularization to the methods that we're using. And then the last piece is a really powerful tool that I and David and other collaborators have been working on for some time now called Posterior Summarization. So once we've actually fit our model, potentially a complicated non-parametric model, how do we actually distill some insights from that model? And how do we do that carefully in a way that's going to avoid problems of using the data multiple times, say by fitting multiple models for different purposes? Okay. So that's going to be kind of the motivation here. Again, just Bayesian modeling being really effective for estimating heterogeneous treatment effects. Like I pointed out, Bayes estimates from these models actually have really good frequentist operating characteristics. We spent a lot of time validating that in simulations. Not necessarily a frequentist statistician myself, but I do recommend methods for people to use over and over and over again, in which case we want them to have good frequency performance. And that's true of the methods we're going to talk about today. So like I said, we're going to have sort of these three considerations. The first one, model parameterization. The take home here is really going to be when you can, isolate the thing that you're trying to estimate and make it a parameter in your model. Okay. Prior specification. Prior distributions are important for encoding beliefs, things like plausible ranges for treatment effects, plausible variation in treatment effects across populations, but also for just sort of generically applying regularization. And the big take home I want you to have from this portion of the talk, or one of the big take homes, is really that regularization that ignores selection when we don't have something like a randomized controlled trial can be a disaster. Okay. And then finally, posterior summarization solves, and solves this in quotes because it's in some sense not a solvable problem, it's solving the Bayesian analog of the post-selection inference problem. Okay, so what happens when we use the data to select a model or a summary and then try to make inference using the same data? It's going to help us focus on stable estimates, and it's going to help us get actionable insights for potentially complicated models. Okay. So before I jump right in, I'm just going to sort of cover some generic identifying assumptions and some notation here. So if we start at the top and work our way down, we're going to be thinking about binary treatments for most of this, although we'll sort of touch on continuous treatments as well. This notation here, yi of 0, yi of 1, those are two potential outcomes. Yi of 0 is going to be the outcome that we see under control when the treatment is assigned to 0 for unit I. Yi of 1 is going to be the same thing, only when that unit is treated. Okay, so those are our two potential outcomes. Zi here is going to be an indicator for treatment, or we're talking about continuous variables, just the treatment variable itself. Xi are going to be just a vector of covariates, things that we want to condition on. These might include treatment effect moderators. They might include predictors of the response. They might include confounders. Most of the time, they're going to include all three. We're going to start by making the assumption that our treatment variable is conditionally independent of the potential outcomes given covariates here. Essentially, that's just assuming that we've measured all the confounders, variables that causally influence both the outcome and the received treatment. Okay? That holds trivially in a randomized controlled trial. In an observational study where we didn't randomly assign treatment, we need to make some assumptions about the data to get there. Okay? This positivity condition down here just says that the probability that we receive treatment at every value for x is bounded between 0 and 1. That's really just sort of a logical condition to be able to define treatment effects. The treatment effects are going to be defined as the contrast between what happens under treatment and control. So you need to be at points in covariate space where everybody could possibly get treated or possibly be in the control condition. Okay? So under those two conditions, we take the problem of causal inference and really turn it into a problem of regression or prediction, okay? So the probability distribution of the potential outcomes here can be identified with the conditional distribution of y given z and x. And we can define this parameter down here, which we're going to spend a lot of time talking about, the conditional average treatment effect function, which is just going to be the expected value of the difference between the potential outcomes under treatment and the potential outcomes under control, given the covariates here. Under these assumptions, I can sort of pass that expectation through and turn that into the difference between the expected value of y given x and z is 1, and the expected value of y given x and z is equal to 0. Okay? Estimating this guy right here, right, this function, e of y given x and z, that's regression, right? Regression is maybe not easy, but something that we feel like we know how to do. But we're going to talk a little bit about why sort of naive regression approaches adapted to this setting can fail pretty badly. Okay. Any questions about the notation stuff before we go on? I'm just going to kind of assume this stuff and then go on. Yeah.
Could you go over Z, please?
Z is a treatment indicator. So Z would be 1 if you're treated and 0 if you're control. When we talk about continuous treatments, it's just the value of the treatment.
And then positivity is when 0 is from 0. Sorry, Z is from 0 to 1.
Yeah, positivity here would be for a binary treatment, right? So all this condition says is that whatever your covariate vector is, wherever you are in X space, there's some probability that you're treated and there's some probability that you're not. Okay, so I want to start by talking about how we're going to parameterize our model. Okay, so we've taken this problem of causal inference, mapped it into a regression setting, we want to write down a regression model. How do we parameterize that model? And actually, the first thing we're going to do is forget about regression entirely. Okay, so I'm going to assume that I have a randomized controlled trial, so I randomize people to treatment or control, and I'm going to assume that I don't have any covariates that I care about. Okay, so the simplest possible setting. A model for the outcomes in a randomized controlled trial like this might look something like this. So we have 2 conditional distributions, the outcomes given the control condition, the outcomes in the treated condition. We're going to assume that both of those come from some normal distribution. The normal distribution has mean mu0 and mu1 with a control and a treatment condition respectively. Okay. I'm going to assume that those 2 normal distributions have the same variance there. That's an essential. It just is a little bit easier to reduce the notation. So the estimate of interest here is going to be the difference in expected outcomes under treatment and control, right? So the difference between mu1 and mu0. Okay, easy peasy. So if we just decide to write down our priors in this way, if we decide to write down independent priors for mu0 and mu1, say they come from some normal distributions with mean phi 1 or 0, and then delta 1 or 0 for the variance, what does that mean for the prior distribution on the thing that we care about? Which again, remember, it's just this tau, right? The average, the difference in averages between treatment and control. Well, since those priors are independent, what it means is that our induced prior on tau is going to be normal with mean phi 1 minus phi 0, and variance delta 0 plus delta 1. Okay? So the prior variance, the regularization that we impose on the treatment effect, is less than the regularization we impose on the expected outcomes under treatment, the expected outcomes under control. Okay? If you have a lot of data, this doesn't matter, right? If you have a lot of data and the noise is relatively low, you're going to be fine. If you don't, then what you're doing here is you're applying very little regularization to this estimate of the treatment effects. And oftentimes, we actually know a lot about treatment effects. We might know things like they tend to be small on average. They tend to be, in particular, smaller than the variability in the outcomes. And that's not encoded in this prior distribution, right? We wrote down this prior independence. We wrote down this independent prior for the outcomes under the treatment and control conditions. And the effect of that is that we induce a prior on the thing that we care about that doesn't actually make a lot of sense, okay? So what do we do instead? Well, we can reparameterize our model, okay? So now instead of having mu0 and mu1 as the parameters that I'm putting priors on, I can put priors on mu, which in this case is going to be the expected value of y under the control condition. And then we can actually write the expected outcomes in the treatment condition as mu plus tau. So now tau, that treatment effect, is a parameter in the model. Okay? I can express my prior beliefs on tau directly. Okay, I don't need to worry about trying to induce a particular prior. And I can do that independent of the nuisance parameters, which usually we would think about this parameter mu as just a nuisance. It's not actually something we're interested in estimating necessarily. It's just something we have to kind of deal with to estimate tau. Okay. Simple things. If you've ever taken a Bayesian inference class, you've seen this sort of idea, you've seen this sort of thinking. When I started working in this area, most of the popular methods for using Bayesian models to estimate heterogeneous treatment effects were not thinking about the problem in this way. Most of the models were doing one of these two things. So if we go back now to our setting where we have covariates, treatment effect moderators, potentially confounding, we can sort of think about the analogs to those two different approaches. So one way you might think about writing down a non-parametric regression model for heterogeneous effects is basically just doing what we started with before. So we have a regression model for y, okay? So yi is going to be equal to f sub zi of x plus epsilon, okay? So either yi is going to have a conditional mean that's f naught in the control condition or f1 in the treated condition, okay? So what does that mean in terms of the distribution of the data? Well, if we assume no errors here, then we have yi given z is equal to 0 and x coming from, again, just normal distribution of mean f naught of x, f1 of x in the treatment condition. And we have the same problem here, okay? Independent priors on f naught and f1 means that the prior on tau is going to have larger variance than the prior on either f naught or f1, right? As long as those priors are independent, which is not great. But we actually have an even bigger problem. Because we've stepped away from the setting where we're just trying to estimate an average treatment effect, and now we're thinking about estimating heterogeneous treatment effects, regularizing f1 independently and f0 independently is a terrible idea, right? Because those simple forms for f1 and simple forms for f0, when we take the difference, we can get something that is not so simple anymore, right? If f1 has a bump over here and f0 has a bump over here, and I take the difference, now I have two bumps, right, in that treatment effect function. So applying regularization to the two treatment arms independently can be disastrous, and it tends to give you very high variance estimates for conditional average treatment effects. So that's bad news. The other problem is a little bit more subtle. When I write down the model in this fashion, what I'm saying basically is that every variable in that x vector is a potential treatment effect moderator. Oftentimes that's not what we want to do. Sometimes we have variables, oftentimes we have variables in the model either to reduce variance by trying to explain why, or they're in there just because we know that they're confounders. They influence the receipt of treatment and they influence outcomes causally, and that's something we need to adjust for, but we don't necessarily think that variable is going to moderate the treatment effect, okay? So that's not great either. Some of the most popular methods for actually trying to estimate heterogeneous treatment effects with Bayesian models, Bayesian non-parametric models, actually look something a little bit more like this, where instead of this totally separate f0 f1 parameterization, we use parameterization that looks like this. Basically, we just take that vector, z, of the treatment assignments, and we just concatenate it onto the X matrix, right? So you can think about just using the treatment variable as just another covariate. So we call this just another covariate parameterization. Okay? And so now, I have a model where my conditional mean is just given by f of x and z, right? So we're just treating z like another covariate. The conditional distribution for y given z and x just has a normal distribution centered here. The heterogeneous treatment effects we get by plugging in a 1 for z and a 0 for z and then taking the difference to get tau of x. But again, most of the time, for most of the priors that we're going to use on f, we have the same problem. We don't have any direct prior control on tau of x. There are some exceptions for things like particular Gaussian processes. You can sort of work out that this guy's not the Gaussian process. But in general, we actually don't know what the prior we're inducing on tau is going to look like, which should make you a little bit nervous because that means you don't know what kind of regularization you're applying to that function. And we still, again, have no direct prior control over which variables are going to be treatment effect moderators and which ones are just predictive of treatment, predictive of treatment receipts, or both are confounders. Okay? So if we want to have a knob in our model that we can turn to control what's going on, what we want to do is we want to reparameterize, just like we did in the original case where we had an RCT and no covariance, right? So the idea is just to rewrite that function, f of x and z, as mu of x plus tau of w times z. So here I'm writing tau w. W could be all of x, or it could be a subset of x, right? So if I have a subset of variables that I think moderate the treatment, I can use that subset and still have other variables in here, either as controls or to adjust for bounding. So I'll just point out that in the case of a binary treatment Z, this is perfectly general. You can always decompose that f in that way, right? It's trivial. And so what happens now? Well, now we have a model that looks like this. My heterogeneous treatment effects are given by tau w. Okay? So we have direct prior control. And in particular, I can think about carefully specifying a prior distribution on tau to apply the kind of shrinkage regularization that I want to impose on my function, right? To make sure that I'm getting stable estimates, low variance estimates, conservative estimates, shrinking those things back towards homogeneous effects, shrinking them back towards simpler models. Okay? So up until here, I've been sort of prior agnostic in terms of what kind of prior distributions you want to put on mu and tau. Some of the more effective Bayesian non-parametric models out there are built on regression trees, Bayesian additive regression trees. And using Bayesian additive regression tree priors on mu and tau gives us a model that we introduced in this paper here that we call Bayesian causal forms. Okay. So I'm just going to tell you a little bit about how we actually build up a prior distribution using regression trees to give you an idea of the sort of knobs that we can turn. Before I go too much further, though, I just want to point out that this parameterization is a good idea, regardless of whether you want to use Bayesian additive regression trees or some other prior distribution on these functions. Okay. So talking about prior selection, if we want to think about how to build up a regression function using trees, a sum of binary trees, we can do it in the following way. So we're going to have a collection of binary decision trees that look something like this. Okay. Each one of those little trees is going to make a contribution to our prediction. The way that we're going to get the contribution to our prediction is just by taking that covariate vector x and dropping it down the tree. Okay. So I would start up here. I would take a look at x1. If x1 is less than c, I'm going to go to the right. Okay. If x1 is less than d, I'm going to keep going to the right, and then we're going to end up predicting mu3. Right? So we just sort of follow our way down the tree based on those interior binary decision rules. What that decision tree gives me, in combination with the parameters down here in the end nodes, is it gives me this little baby step function, okay, that has 3 steps and 3 levels. And you can see the cuts here corresponding to decision nodes in the tree. Right? So trees are giving us little step functions. Okay. When we build our regression function, we don't necessarily want to use a single tree, just because it's difficult to approximate a generic function with a step function. And we also don't have any real smoothness, right? These mu's are not, are sort of unrelated to each other. Okay. But when we start adding up a whole collection of small regression trees, we actually get some interesting behavior. Okay. So the idea here is that we're going to build up our function f as the sum of a bunch of these regression trees. This was the regression tree I just showed you on the last slide. We can think about composing that with a different regression tree over here, okay, with a different set of splits. That's going to give me a step function that looks something like that in 2D. And what happens when we compose those two things is that we end up with this more complicated step function over here. You could also represent it as a tree, but it would have to be a big, deep tree, okay, which we don't like for various reasons. And the interesting thing here is that inside those step functions, we're going to have some of these shared parameters, right? So you can see that across this top slice here, if you're above E on this axis, right, your prediction is either going to be theta1 plus mu2 or theta1 plus mu1. So if you're up here in this region, if you're here, your predictions are going to be similar because you share that one parameter, okay? So ensembling the trees like this, adding up a bunch of little trees, is going to give us a degree of smoothness in our function estimates, which is desirable behavior, okay? So this little picture is just to kind of illustrate that. If you look at the prediction for these 3 dots, the purple guy, the red guy, and the blue guy, well, red and blue are close together, So over here, they get split across different bottom nodes in that tree. They're on different steps in the step function. Over here, they're on the same step. So what does that mean? Well, it means that they're going to share the contribution of this middle tree and their function value. So the function values for the red dot and the blue dot are going to be correlated. They're going to be positively correlated. Okay. If you compare that to the purple dot, who's further away than the other two, right? Its function value is going to be just uncorrelated with the other two because they share no common parameters, right? And you have theta1 here, theta3 here, mu1 here, and then mu2 or mu3 down here. Okay. So what you can think about that set of trees, that ensemble of trees is doing is it's sort of learning this covariance function. It's telling me how to chop up covariance space so that function value should be highly correlated over here and less correlated over here in a way that's adapted to the data. That kind of data adaptivity is a big reason why Bayesian additive regression trees tend to work better than Gaussian processes with the usual covariance functions. Okay, so if you think about how this representation works, you can sort of start to see where the knobs come in for making sure that I get a simple function. Okay, I can get a simple function by making sure these trees tend to be small, right? If none of these trees ever split, then I would just have a single number, right? I can also make this function relatively simple by making sure that within a tree, these steps are not that far apart. Okay, so none of those steps are particularly big, right, for each one of these trees. The other knob that I have to sort of control what's going on is the number of trees, right? If I only have one tree, then the function can only be so complex, given that I want the trees to be small and these function values close together. Does it kind of make sense? More or less? Okay. So when we're thinking about writing down a bar prior over a function, whether we're doing regression or trying to estimate treatment effects, we're going to have a few considerations. So the number of trees M is typically going to be large. We're going to use a prior on T that's going to put high probability on smaller trees. And then for those parameters down there in the end nodes, we're going to have them following a particular normal distribution so that the function value at a given x has a normal distribution with this variance sigma squared f. Okay. So these guys, that parameter sigma squared f is going to kind of control the likely range of those function values. And the prior on the trees is going to sort of control how not homogeneous, not additive that function is. Right? The deeper those trees go, the more interactions and non-linearities we have. Okay, so going back to the model I was talking about a moment ago, the Bayesian causal forest, how do we use those insights here? Well, if we think about these two functions, they're doing very different things. Okay, so in a setting where we have observational data, that function mu of x is deconfounding for me. Okay, so I might actually want to sort of back off on the regularization of mu to make sure that I'm deconfounding my estimates of tau. Okay, I don't have that on the slide here, but that's a thing that we do in the paper. Really, we want to focus on what we're doing here for tau. So if you take a look at this model and sort of forget the fact that this is a nonlinear function, what do we have? Well, this is just an interaction in a regression model, right? Tau times z. So what do we want to do? Well, we want to make sure that we don't estimate super high order interactions, right? Third, fourth, fifth order interactions are sort of implausible and definitely difficult to estimate, okay? So one of the tweaks we make to the default bar prior is that we put higher probability on smaller tau trees, right? In particular, we increase the probability that a tree does not split at all. So if none of those trees in tau ever split, then we're back to a case where we just have homogeneous treatment effects. That function tau is just flat, okay? If every tree only splits one time, then we have an additive model, and we only have two-way interactions with the treatment, right? So those are reasonable things to shrink backwards, and we control that by putting higher probability of smaller trees in that ensemble. Okay? Like I said, we put higher probability on stumps to get homogeneous effects, stump just being a tree that doesn't split at all. And then we actually use a particular sort of hybrid prior on the scale of the leaf parameters in tau. Again, this is just to sort of control the variability in tau. So these are the sort of knobs that we have when we're using bar priors on tau and mu. Other non-parametric priors will have their own knobs that we can turn. The point here is really just to make sure that we parameterize our model so that we have the ability to do so, right? And then you can use whatever prior you like. I would recommend the bar priors on mu and tau. They seem to work really well. But we're actually not done thinking about priors unless we have a randomized controlled trial. If we have a randomized controlled trial, then this model I wrote up here is going to work very well. You don't really need to do anything else. If you have observational data, right? So if you have confounding that you need to adjust for, we actually need to go on and modify our priors a little bit further, okay? To avoid something that's called regularization induced confounding. It's induced by David and some of his collaborators in this paper in 2016, and we elaborated on in the nonlinear case here. Okay, so why do we need to adjust our priors when we have selection into treatment? The easiest way to think about what's going on is to actually go back to a linear model. Okay, so forget about all that nonlinear, non-parametric stuff for a second. And we're actually going to go back to the case where we're trying to estimate homogeneous treatment effects too. Okay? So now my model for outcomes is just going to be yi is tau zi, so tau is my treatment effect, plus beta times x. So that's going to be the equivalent of my mu of x on the previous slide. And now suppose that that covariate vector x is high dimensional, so I need to regularize my estimates of beta to make sure that they're stable, right? We might even be in a case where p is bigger than n, and we need to apply regularization to be able to estimate anything at all. Okay. So let's take a look at what happens here. So I'm going to apply just the simplest kind of regularization you can think about the covariate vector beta. We're going to give it something called a ridge prior. This prior has a posterior mean that corresponds to ridge regression. That's why we call it a ridge prior. You might be more familiar with ridge regression. We're going to tweak the usual ridge penalty just a little bit and only apply it to beta and not to tau. Okay, so I'm going to have independent priors on beta and tau. Prior on beta is going to be this ridge prior. The prior on tau is going to be flat. So I'm actually not applying any regularization at all to the parameter tau. And now we just want to think about what effect this prior distribution, this ridge prior on beta, has on my estimation of tau. Okay. We're going to use the posterior mean for tau as our estimator. In that case, we can actually write down explicitly what the bias in estimating tau is going to be when we apply that ridge prior to beta. And that bias looks like this. It has a few different pieces. This lambda, that's the ridge parameter. Okay. So bigger lambdas, more regularization on beta. Okay. Z, you remember, was the vector of treatment assignments, treatment variables. Z minus the Z tilde is the residuals in an estimate of the ridge regression here. Okay. So if we think about trying to estimate Z using a ridge regression linear in this linear model here, we would have estimates, gamma tilde lambda, and predictions, Z tilde lambda. Okay. So that's this term out front here. What you'll notice about this inner term here is that it's going to tend to be small when Z is well predicted linearly by X in this ridge regression, right? These are the residuals. As they get tiny, this whole thing is going to get big. These guys are going to be tiny when we have strong confounding, all right? But then look at this term on the right. So this term on the right is the inner product of beta from the outcome model, right? So the true beta is here. And these ridge estimates in the ridge regression of Z on X. Okay. In general, unless those two covariate vectors happen to be orthogonal, that's going to be a non-zero number. We don't know the sign. We don't know the magnitude. We don't know the bias that we're imposing on our estimates of the treatment effects unless we know something about the true beta. So of course we don't, right? So that prior distribution, that regularization we apply on beta is going to induce bias on our estimate of the treatment effect, the thing that we actually care about, of unknown magnitude and direction. That's bad news, right? Typically, if we were going to regularize, apply some regularization, apply some bias to our estimates of tau, we'd want to do things like pull it back towards 0 to make sure the variability isn't too high, or be conservative, right? So what we see here is that just naively applying regularization is kind of a disaster. We're inducing bias, and we don't know how big it is, we don't know what direction it is. Fortunately, there's a very simple fix, and that fix is to actually expand the model to make sure that our function, in this case, this linear function here, does not penalize variation in the direction of the conditional expected value of z. Okay? So how do we do that? It's really easy. What we do is we actually take the data that we have on z and x, we get an estimate, z hat, for the conditional expected value of z. Okay? In the case of a binary treatment, that's just the propensity score. And all we need to do is drop it in the model, okay, as an additional covariate. I'm going to use the same ridge priors on beta. And I'm not going to apply any regularization to tau. I'm not going to apply any regularization here to this parameter. This function f of x and z, whatever it is, we're going to let it vary freely along both of those directions, z and its conditional expected value z hat, or estimate of that. Okay. What happens when I do that? What happens to that bias equation? The formula of the bias equation looks the same. Okay. We still have those pieces. We have the lambda. We have those residuals. We have these ridge coefficients, except now these ridge coefficients here are from a ridge regression of z on z hat and x. Okay. So you can sort of see immediately what's happening here. If we have a good prediction of z in z hat, all these coefficients here are going to tend to be 0, right? If we're controlling, adjusting for a good estimate for the true conditional expected value of z, these guys are going to tend to be 0. This inner product is going to tend to be 0. The bias is going to tend to be low, right? Does that make sense? There are different ways we might have done that, but this is an easy one, to just drop in an estimate of z hat as a covariate. Okay. Just a couple things to point out here. There's nothing special about the ridge prior or the linear model in this case. This kind of regularization-induced confounding is very easy to produce with nonlinear models and nonlinear data generating processes. We do it a bunch up here in BCF paper. In essence, what's going on here is that since z is a proxy for the expected value of z given x, if the prior on f penalizes variation in the direction of the expected value of z given x, the prior is going to encourage misattributing that variation in f to z, right? This is not a Bayes problem, it's a generic regularization problem. Okay. The solution is also generic. In general, when we're trying to use these sort of machine learning, Bayesian, non-parametric, whatever models for estimating heterogeneous treatment effects, just include an estimate of z hat as a covariate. In the case of a binary treatment, all we're saying is estimate the propensity score, include that as a covariate in your model, right? It's not the only way to do this, right? In a linear model in particular, you could actually just replace z with z minus z hat and do the same thing, okay? But this is sort of a generic formula that doesn't even require you necessarily to tinker with software, okay? In our paper where we introduced BCF, that model we actually use looks something like this. That function mu takes as inputs x and z hat, okay? So we're going to let those trees split not along just the axes of z, but also along an axis that's defined by the propensity score, the estimated propensity score here. We evaluate this in the paper. I'm not going to bore you with a bunch of simulations, but including the propensity score typically doesn't hurt. And often it helps debias our estimates an awful lot. In particular, in this case, where selection into treatment is based on expected outcomes under control, right? So if I think that I'm going to have high blood pressure, unless I take blood pressure medication, I am more likely to take blood pressure medication, okay? So this is sort of a selection structure that I think is really common in practice. And it's really easy to show that when you have that sort of targeted selection into treatments, the bias due to regularization-induced confounding is going to be extreme unless you include an estimate of the propensity score in general. Okay? Any questions there? Yeah, that's a great question. So the good news is you can do whatever you want to get your estimate z hat. right? When I'm doing Bayesian inference in a model like this, all my inference is conditional on X and Z, right? So you can think about adding Z hat as really just any other transformation you might get with your covariates. So what you'd like to do is whatever your favorite machine learning methods are, just try them out on predicting Z given X. Right? Evaluate them in the standard way, cross-validation, do whatever, pick one and plug it in. Right? So anything you might do in a generic sort of classification problem or a regression problem, you can do here. Yeah.
You don't have the hat, you still need X. You still need conditional on X.
Yeah, that Z hat is a function of X. Yeah. Yeah, so that's a good point. So, you know, the notation I use here is sort of obscuring that fact, right? That U of X, you know, I don't necessarily need to have the extra ordinate here, right? Because Z hat is just another function of X, right? So it's just like taking two of my covariates and multiplying them together. I haven't actually changed the inputs to that function, right? Yeah. Any other questions there? I'll just point out that we get this sort of question a lot. You know, once I do that, once I include that estimate of the propensity score in there, don't I need to think about that as a parameter and give it another prior and go through all this exercise? And the answer to that is no. Because again, all my inference is conditional on X and Z in this setting. And all I'm doing, you can think about this as adding a covariate to the regression problem. You can also think about this as just changing that tree prior that I'm applying to mu in this case to let it split, not just along axes defined by X, but also along the axis defined by the propensity score. Right? So it's going to be sort of the analog of including Z hat in the regression model up here, and then not applying regularization to V. We're just giving it another axis. Okay. So we'll move on now to talk about posterior summarization. So if we've thought carefully about our Bayesian non-parametric model, we've specified our prior carefully, we've included an estimate of the propensity score to make sure that our estimates are not terribly biased. We fit that model, we get estimates of, if we go back to our BCF model here, we get estimates of this thing. We get back posterior samples of this function tau. We can evaluate that at any value of W that we want. But now what? What are we going to do with that, right? So we can get estimates for conditional average treatment effects, but we need to sort of map that onto something we can explain to maybe our scientific collaborators. We need to map that onto policy questions. We need to map that onto scientific questions, and that problem can be a little bit challenging. Okay. So the idea here is that I have a posterior distribution over that complicated object. I have it sort of written here generically as G, but you can think about G as tau. Okay. And the idea here is that if I want a more interpretable model, right? If I fit this model with, say, a linear model in here, so maybe instead of tau W, it's W times tau, and tau are just regression coefficients, and I have to think about those. Maybe I specify an additive model here, right? So that that function tau separates into additive components in each one of the moderators, and then I can read off these partial effects or these adjusted effects of the moderators. Maybe tau is itself defining subgroups, like a step function, something that's simpler than what I actually estimated. Any one of those would be more interpretable and possibly more appropriate for answering different questions about how treatment effects vary. Okay. But once I start trying to fit different models, right? So if I fit a model that's linear here, if I fit a model that's additive here, if I fit a model that has a tau defined by subgroups that I pick post hoc, you run into this issue of using the data over and over and over again, of refitting models over and over again. And the problem is that you don't have valid posterior inference anymore, right? I'm using my data to pick my models, and each one of those posterior distributions that I obtain assume that the model was affixed ahead of time. Right? So instead of doing that, instead of trying to refit models that are of different forms or simpler than the non-parametric model that I really want to fit, we're going to use this technique of posterior summarization to be able to answer all those questions simultaneously. analysis. Okay? So the idea here in posterior summarization is pretty straightforward. We're going to think about some function we want to estimate g. You can think about g as tau again. What we want to do is we want to examine the best simple approximation to the true function g. Right? What do we actually think we get when we fit a linear model? We hope we're getting the best linear approximation to the true data generating process, right? That's sort of the generic comment. Here we're just operationalizing that in the context of this non-parametric model, okay? So best is something I get to define, okay, by some discrepancy metric. And of course, we don't know what the true function is, but we're going to use our inferred tau as a proxy for the truth, right? So if we're willing to make inference using the original big model, we're saying that we're willing to let that tau stand in as a proxy for the truth, right? So the idea here is very simple. I'm going to get posterior samples of my function g, tau. And then I'm going to define a class of simple or interpretable approximations, gamma, to that function g. Okay? So maybe I want to approximate it with a linear function, an additive function, a step function with big steps, correspond to a subgroup analysis. I get to pick that, and I get to pick as many of those as I want, so I don't have to do this just once. And I'm going to actually make inference on this parameter here that I'm calling little gamma. Little gamma is going to solve this optimization problem. We want to minimize some discrepancy between g and gamma at some values for the inputs to g. Okay? And we want to do that subject to some penalty over here. We don't necessarily have a penalty over here, but oftentimes we do. This penalty here is going to measure complexity. Complexity could be how wiggly the functions are in an additive approximation. Complexity here could be the number of non-zero coefficients in a linear approximation, etc. It could be the size or the structure of the subgroups if we're trying to do a subgroup analysis. But we get to pick both of those things. Not only do we get to pick both of those things, but we're free to vary them. We're free to choose different penalties. We're free to choose different weights between the penalty here and the discrepancy function. We're free to sub in different discrepancy functions. All of this stuff is happening post hoc after we fit the model, right? So there's no way to use the data multiple times. And we're free to look at as many posterior summers as we want, okay? So we can get a posterior distribution for gamma by solving this optimization problem for each draw. If we want to get a point estimate for gamma, we can actually sort of invert, or we can actually bring inside here an expected value. And this you can show would be the Bayes estimate under a loss function that looks like this guy here. Okay. Oftentimes when this discrepancy function is something like squared error, this is going to be an easy optimization problem to solve. Okay. And you can use existing off-the-shelf software routines to do it. Okay, so what do posterior summaries do for me? The first thing they do is sort of obvious. If I pick them carefully, they're going to be more interpretable than the original model. Okay, so we can take this framework of posterior summarization and derive as special cases subgroup analysis, linear additive sparse approximations to the truth, and they can be targeted to scientific questions. Okay, so we'll see an example of that in a second. The other thing they do for me is they get rid of the need to fit multiple models for different questions, right? I don't need to fit a model that's linear. I don't need to fit a model that's additive. I don't need to fit a model that is based on different subgroups. And that's going to sort of resolve these post-selection inference issues. It's going to give me coherent Bayesian inference over all these different quantities simultaneously with one fit to the data. Okay? Oftentimes, these posterior summaries are more stable. Okay? So if you spend any time trying to estimate heterogeneous treatment effects, what you're going to see is that if you start comparing individual level treatment effect estimates, they're very, very noisy. There just aren't that many people in the world that look like you, right, on all these different dimensions. But if we aggregate those up to subgroups, those estimates get a little bit more stable. If we try to approximate them with something that's additive or linear, we tend to get estimates that are a little bit more stable. You can sort of think about it as having fewer degrees of freedom than you had in the original model. So they're going to tend to be more stable, more well estimated, and more precise. Okay, so you're going to get, you can think of it as some improved power with a lot of quotes. Okay. And finally, these posterior summaries, they're going to come with valid Bayesian measures of uncertainty. I can look at those posterior distributions and they're meaningful, right? As opposed to refitting a bunch of different models, looking at a bunch of different posteriors, each one of which is assuming that the model you fit was true and correct and fixed before you saw the data. So I just want to give you guys an example of how I use this in my own applied work. This is a big randomized controlled trial I was involved in, conducted based here at UT, called the National Study of Learning Mindsets. So the idea here was to evaluate an educational intervention designed to instill in students that they have the ability to acquire new skills. Okay? That belief that you have the ability to acquire new skills is called a growth mindset, right? I can learn that. Okay? There's extensive evidence that on average, students who have a growth mindset perform better than students who have what's called a fixed mindset. You can think about that as like the belief that, oh, I'm just not a math person. It's just not in me to know how to do math, and then I don't learn math. Okay? So there's a lot of evidence that these things tended to work on average. There were some interesting questions about how the effects of a mindset intervention would vary across different populations in different contexts. Okay? So the National Study of Learning Mindsets took a mindset intervention that was known to work, known to produce effects on average based on prior work, did a randomized controlled trial in a probability sample of 65 high schools across the country. Okay, so a representative sample that touched, this particular sample we're going to look at today, touched over 11,000 ninth grade students. And this study was specifically designed to see if those effects varied by contexts. Okay, so context here, there were two that were particularly interesting. The first one was baseline levels of growth mindset beliefs. Okay, so if I think I can learn, but the people around me don't think I can, maybe it's going to inhibit the effect of the intervention. Okay. And then the other context factor was this measure of overall school quality or achievement. Okay? And there were some interesting hypotheses about how the overall level of school achievement would influence the treatment effects. One hypothesis said that the treatment effects would be higher at the middle levels of achievement. At the lower levels of achievement, maybe things are just so rough that this little intervention can't do anything. At the highest level of achievement, maybe you don't actually need it. Maybe there's already growth mindset beliefs and practices being exploited there already. Okay, so maybe it gets to kind of ceiling effects. The other hypothesis basically said that it looks linear-ish, right? That you would see the largest effects in the lowest achieving schools, and they would sort of fall off as you got to the higher achieving schools where growth mindsets were already pervasive. Yeah.
Yeah, I was a little bit confused about this level of growth mindset. We talk about I think it's unit is has a higher growth mindset, but the people around him doesn't believe it. But yeah, we don't assume any interference, right?
No, yes, we're going to assume there's no interference. These measures are school level measures, and they're all taken pre-treatment. So in particular, this measure of baseline level of growth mindset beliefs is actually a measure of challenge seeking. So the exercise here is to let students build their own math homework and then measure how many hard problems they take versus easy problems. Yeah. Yeah, interference is a natural thing to worry about in this setting. There are some reasons to believe it's not a concern. We can talk about those at the end. But yeah, these are both pre-treatment measures at the school level, right? So we're interested in how the treatment affects students in these contexts. Yeah.
Could you go over the two hypotheses again? The linear one?
Yeah, so the first hypothesis basically said that if we looked at a plot of the treatment effect by achievement, it would look like a U. So you'd have the least effectiveness of treatment in the lower achieving schools and in the higher achieving schools, right? In the lower achieving schools, just because things are so bad, you can't actually move the needle. In the higher achieving schools, because of these sort of ceiling effects, right? You're already doing really well. You're already getting straight A's. What are we actually going to do, right? The other hypothesis basically said you would see the highest treatment effects in the lower achieving schools because you're hitting the students that need it the most. So different hypotheses. You can already sort of start to see how difficult it's going to be to take a non-parametric model and pull out insights about each of those things when you're allowing for general nonlinearities and interactions and everything else, right? So let me show you how we used posterior summarization to answer those questions. The first thing we did was the first thing I did was a subgroup analysis. Okay. So in this case, my discrepancy metric is something like squared error. The approximation I'm going to use is again, another regression tree, except I'm going to fit this regression tree to my estimated tau. Okay. And so what that's going to do is it's going to show me a partition of the moderators that's going to separate the students, the schools in this case, into groups that are sort of maximally different on that treatment effect. Does that make sense? Right, but the idea here is that I'm fitting within. Okay, that's going to give me the tree structure. Then once I have the tree structure, that's going to give me subgroups. In this case, I get 3 subgroups. Inside of those 3 subgroups, I can look at the posterior distribution for the subgroup average treatment effects. Okay, so let me just kind of step through what this tree is showing me here. The first variable that it cut on was that school level achievement variable. Okay. The second variable it cut on was this measure norms. This is a measure of baseline mindset beliefs. Right? These values here are population quantiles. So what's happening here is that first split actually peels off those high achieving schools. We estimate a conditional average treatment effect that's small. It's about 0.01 GPA points. Okay? It has a posterior distribution that looks like this over here in the green. And we can see that the treatment was not very effective there, right? In fact, we probably wouldn't even want to say much about it being non-zero. If we keep going down the tree that's defining my subgroups, I go down here to my norms. I didn't talk too much about the hypotheses behind baseline mindset beliefs or challenge-seeking norms. But the idea is just that if the people around me have growth mindset beliefs, it's going to sort of bolster my own growth mindset beliefs and make the treatment more effective. Okay. And in fact, we see that's what's happening here in these subgroups inside those lower achieving schools. Okay, so the cut here is actually right about at the median. Okay, so we have these lower achieving, low norm schools with conditional average treatment effects of about 0.32. So about double what we saw in this group. A posterior distribution that's shifted to the right even more. Okay, but what's really interesting is this subgroup down here. In this subgroup down here, these are the schools that are lower achieving. Okay, so not low achieving, but the bottom 2 terciles. But they have high levels of mindset norms. And we see large treatment effects there, conditional average treatment effects of about 0.07 GPA points for an intervention that's light touch and outcomes that are measured a year later. Okay. I can keep going. I can keep growing my tree and see if there are other subgroups that are interesting here too. Okay. So I can look at, for example, the posterior, not just for the conditional average treatment effects themselves, but actually the difference between different groups. So here I'm showing you in this plot the posterior distribution of the difference in subgroup average treatment effects between these 2 guys. Okay. So basically, that's giving me an idea of how likely it is that this difference is meaningful or real, right? If I keep growing my tree, I get another cut down here that's actually on achievement. Down near that first tercile, I separate out these 2 subgroups here. We're less confident that there actually is a difference here. And so I probably prefer to look at this set of subgroups here. So that's one way to try to get at how the treatment effects are varying across different populations. And in particular, it's a useful way to think about the variation in achievement. When we're thinking about how the variation in levels of mindset norms works, we're interested in that kind of variation for 2 reasons. One, it's sort of scientifically interesting. 2, that's actually something that we could intervene on, right? We could design an intervention to sort of raise the level of baseline mindset beliefs in the school. Maybe we try to get teachers to believe more, to incorporate more mindset practices. That's an intervention that we're working on right now. But if we want to understand how that works, what we really want to know is whether the effect of a little change in mindset norms is going to be the same across schools, or if it's going to vary across schools. Basically, we want to know, is there an interaction between mindset norms and these other treatment effect modulators? Okay? And this subgroup analysis doesn't tell me that. Okay? It doesn't tell me whether there's actually an interaction, It's just trying to approximate that complicated overall tau with a regression tree. Okay. So what we can do instead is we can fit an additive approximation to that function tau. So what we're going to have is we're going to have an offset that's going to end up being the sample average treatment effect, and then or an intercept. That's the sample average treatment effect, and then these offsets here, one offset for each of the treatment effect moderators. Okay, and because that function is additive, my approximation here is additive. I can directly read off those partial effects of treatment, right? So what is the effect of a small increase in norms holding constant the school achievement, which is not a variable we could plausibly intervene on, okay? And so I can not only get that summary, but I can get that summary plus a measure of how, a measure of fidelity, right? So how close is this approximation actually to tau? Okay. What we use here is just this sort of pseudo R-squared measure. You can interpret that as R-squared in a regular regression model. Okay. So if we fit an additive approximation, we get results that look something like this. There's one extra moderator here I'm not showing you. It's the percentage of stereotyped minorities in the school. Leaving that out, there's not really anything going on there. We see that we have these two partial effect curves. Okay. A couple things to keep in mind about these partial effect curves. Those are giving you offsets from the sample average treatment effect, which is positive. Okay. So the fact that these guys are sitting around 0 when they go negative is not a big deal. It's sort of relative to average treatment effects. And these bands are pointwise bands, but what they don't tell me directly is whether we're sort of confident that the function is increasing here and decreasing here. Different plots to do that. I'm not going to show you those. I'm not going to have time. But what we see is that we get this additive approximation here. We see sort of a hint of that U shape in school level achievement. A lot of uncertainty down here because you have just a handful of schools with the lowest level of achievement. Those also happen to be schools that have the highest percentage of stereotype minorities for reasons. If we look at the partial effect of baseline mindset norms, we see this really interesting nonlinear pattern where it's kind of flat down here. Again, a lot of uncertainty at the lowest levels. It increases a lot through here, and then it kind of levels off at the highest levels of norms. Okay, but actually quite a bit of variability here. And so if you were able to take a school that was sort of down here in the lower levels of norms and move the needle a little bit up here, we see increases in that treatment effects that are comparable to some of those subgroup average treatment effects we saw before. On the right-hand side here, I'm plotting the posterior distribution of that R-squared measure. We'd like that to be close to 1. If that thing is close to 1, then my additive approximation here is actually close to the tau I fit. And then I could actually use that additive approximation to make inference about tau, right? So here we can see that R-squared measure is a little bit low. But one of the things that we talked about when we introduced posterior summaries, right, was here, this penalty term here, okay? This first plot, I've applied a penalty that says whatever I'm estimating for these additive effects, I want it to be smooth, okay? If we back that off, we can actually get a closer approximation. The functions get a little bit wiggly and uglier, although if you sort of squint, I mean, they're telling you the same story, right? It's two additive functions. My approximation is really good. So this additive approximation explains, I think it's about 94% of the variance in the original function. I would be comfortable using this additive model to make inference about tau. And what I'm seeing here is that even controlling for or holding constant overall levels of school achievement and the minority composition of the schools, I would predict an increase in treatment effects if I could intervene on norms here. Okay. You have to be a little bit careful, right? Because that's not, we can't really make causal statements here, but it is at least suggestive that if we could intervene on baseline mindset norms, increase norms, we can increase the effectiveness of the individual level, student level mindset treatment. We've actually gone on and showed that in ongoing work here at UT. Okay. Lots of other things you can do with posterior summarization. One, you can do interaction detection. So if I fit that additive approximation and it was garbage and I couldn't make it better, what's that telling me? It's telling me that I'm probably missing an interaction that was captured in the true posterior, okay, so that I can go looking for that. In this paper here, we show you all how to do that. Sensitivity to control function specification. This is sort of an interesting case. How do I expect removing confounders or control terms, or adding nonlinear terms, or taking nonlinear terms away? How do I expect that to change my estimate of treatment effects? That's kind of a cool application of posterior summarization. Again, solves a lot of problems that people try to solve right now with big regression tables. I can use it to try to explain what my model is doing. Explanations here in very warranted air quotes. But if you're familiar with Lime, really popular method for explainability, that's actually, you can sort of think about that as a posterior summary with a linear model, but in a neighborhood of x, right? So tell me what the partial derivatives are around that function in a neighborhood of x, which people use as a, an explainability index. I hit time, so I'll stop there. Lots of interesting stuff to do here. I referenced some papers. I don't have my reference slide. I just have a thank you slide. But that's my website, and I'm here in the room. So if you guys want more information, please just let me know. Thank you.
Questions? Any questions online first? Okay, well, one quick question from my end. So if you can fit this in a complex function, and you can always get back to like linear summaries, does this mean that?
Is there something?
With higher OLS, always fit something complex and then go back to a linear statement?
Hi, David.
Oh, there he is. Hey, Max. I mean, so maybe. I don't do a whole lot of OLS, except when I do. But yeah, certainly, you know, if I could approximate this guy with my discrepancy here was just the distance between a linear model and my complicated fit. Oftentimes, you're going to get back a linear summary that looks like the OLS coefficients. The interpretation is a little bit different. OLS has some particular properties that your overall global model might not have. I don't see a lot of reason to do OLS. I don't do a lot of it anymore. Right, once we sort of move past trying to estimate just average treatment effects, you know, once you start applying regularization, it's over. It's over for OLS anyway. But you can get back a lot of the virtues of interpretability, right, that might lead you to do something like OLS using posterior summarization. Yeah.
Not really a question, but I was just shocked to see that the growth mindset intervention study was something connected at UT, because this is a study with a study for STA 301, which is data science class. So, nowhere as detailed as this. All we covered was the RCT part of it, none of the Bayesian model or posterior summarization. But as a beginner who's interested in statistics, I'll be 100% honest. All I understood was about 10% of it. I got like the posterior summarization, a little bit like the big picture, but what would you recommend for a beginner to expand their statistics knowledge?
I mean, you started in Stat 301, so that's a good place to go. I would say keep going. And we should talk. We should talk afterwards. Yeah.
At the beginning of the learning mindset example, you mentioned interference is not something we worry about here.
Yeah.
I'd just be curious why that is.
Yeah. So there's a couple pieces to it. So the first one is that the direct effects of the treatment are small, right? That's something you would expect. In general, it's hard to move the needle on people's beliefs. In particular, when you're looking at effects, knock-on effects. So the intervention was delivered at the beginning of 9th grade. The treatment effects I showed you were on their GPA at the end of 9th grade, so like an academic year on. So you expect those effects to be small. The other thing that you learn when you start talking to the people that design these interventions is that little permutations in how you present the information can make a big difference in whether or not it actually works. Not a psychologist, can't really explain the psychology, but it's really easy to design an intervention that seems like it should work, but the wording is just wrong, or it's not sort of framed in the right way to the right population, and it kind of doesn't work. So now think about where you would get the interference. Think about where you get the spillover, right? You would get the spillover from, say, I have the mindset intervention, I get all excited, and I go tell you that your brain is like a muscle, and that if you work it, you can learn stuff. I'm probably not going to be able to deliver it as well as that trained psychologist was, right? So whatever that spillover effect is, we expect it, if it's there, we expect it to be small. So that's one reason why. The other reason we don't worry about it so much is that to the extent that you do have spillover, it's going to attenuate the treatment effects, right? If that treatment has a direct effect on me and an indirect effect on you, we sort of expect it to be positive, right? It's hard to imagine that this little intervention that tells you your brain is like a muscle is going to suddenly make you not believe that your brain is like a muscle, right? So to the extent that there is spillover, we think that it would attenuate the treatment effects and that our estimates are probably conservative. That's why I don't worry about it so much. It's a great question, though. Yeah.
Lately, we've been like doing some guys with priors on those like cache processes and like business functions. It's kind of like a organization that you doing like step function to like. And I want to know like how this gets better and how this really like do posterior summarization. Does it get better also like how this like all this process is working right now?
Yeah, that's a great question. So Ricky asked, so we've been sort of working on variations of these sort of basic tree ensembles here that do various different things.
Soft BART?
Yeah, so soft BART that Enrique mentioned is basically a way that instead of making deterministic decisions here, we make probabilistic decisions. That has the effect of smoothing out these steps and giving me a smoother function estimate. The other thing we've done is actually replace these single values in the end nodes with functions. So you can think about having a variable like time down here in the end nodes here, so that you want a function that's smooth in time, but still have this tree structure and the other covariates. That's a different model we've worked on. So it really depends on the context. So you can actually get a lot of the benefits of smoothing from fitting a model like this and then applying the smoothing in your posterior summary, right? Yeah. That's what I'm doing down here, yeah, right? In both cases, whatever the penalty is, the true function is the smooth, right? Even though I'm using this smooth and spline approximation to the truth. So in some cases, you can get the benefits post hoc and posterior summarization, which is nice because it saves you from having to do, those other models, harder, more complicated models, more difficult to fit, right? Just computationally intensive. That's not universally the case. And the other thing that you get out of some of those models is a prior that's a little bit easier to understand. So if I think that function is supposed to be smoothly varying in one variable, it makes sense to have a prior that lets me specify the degree of smoothness or try to infer the degree of smoothness. It's not something that's super easy to do for like one specific coordinate in a bar ensemble. So the short answer is it helps sometimes. In terms of the summaries, it opens up like a whole bunch of different things that you can do for the posterior summarization. It's really, the stuff that I showed you today is baby summaries. There's a whole lot of interesting work that can be done.
All right, thanks, Jared.